Okay, we ever take another integral. This one was from MIT 2016, problem 17. We have the integral of e to the 2016x plus 6048x dx. Okay, I was looking back at some of the MIT integration bee problems, and I think this is my favorite one from 2016. They actually had a lot of easy problems on there and some common ones, so there wasn't too many to choose from, but I think this one was my favorite. So to get started with this, the first thing I want to deal with, it's kind of weird having 6048 here. One thing we'll want to notice about that is 6048 is just going to be the same thing as 3 times 2016. So I think we can use this, but first what I want to do, I kind of don't like having this complicated exponent here broken up on the plus sign. So what we can do is I can kind of rewrite this. So I'm going to split it. We can turn this into multiplication. So I can write it as e to the e 2016x. And then for this other one, I could write this as e to the 6048x, but I think what I'll do is just use this right away. And I can actually write it as e to the 2016x cubed dx. And this way, I think it's going to help us with a u substitution, because what I can do is I can substitute for this, call this u right here, but then this is also going to be u over here. So let's see how this is going to go. If I just say u is going to be e 2016x, I'll take a derivative on this. du is going to be e 2016x, but then chain rule, we have to bring a 2016 out over here, and we'll have a dx. So I think in order to make this substitution work, before I actually do it, let's set it up. So I want to create the du at the end. So I'm going to multiply in a 2016 here that we don't have anywhere. I don't want to change it, so I'll have to multiply a 1 over 2016 in front. So I'm just multiplying by 1. Then I'm going to take one copy of this over here, and we'll have just e 2016x dx. So now we have our du right here. I used one copy of this here, so we have two copies of it left over. So we'll right over here, we'll have e 2016x all squared. Sorry about that. And then over here, we'll write in this stuff. And now I think we're all set up for the substitution. We'll keep this 1 over 2016 in front. This right here just becomes, but this is u, this is going to become e to the u. This here is used, this becomes u squared. And then everything here we set up to be du. But now with what we have right here, this is in good shape for integration by parts. We'll use the di method on this over to the right. So what I'm going to do is let's just differentiate u squared and integrate e to the u. We're going to have to do this a few times. So let's see, when I differentiate u squared, we get 2u. Do it again, we're going to have a 2. Do it one more time, we get a 0. Integrate e to the u, we get e to the u, e to the u, e to the u, e to the u, on and on forever. Now we can actually stop here because we have a 0. So then from here, what we're going to want is we have our solution in u on the diagonals. So when I write this down, what I can do is let's factor. We have e to the u in common, so I can factor out e to the u, put it over 2016, and then just kind of sum up all this stuff. It's going to be u squared minus 2u plus 2, and then all we're going to need to do is just back substitute this in order to finish it off. Okay, so now one thing before I back substitute, for this u squared right here, just to be clear, we can kind of put it back. We can write it like this, e 2016 squared, but I can also put this back, multiply this back in. So for u squared, I can write it as e to the 32x. So putting everything back, what we're going to have for our solution is just going to be e to the e 2016x over 2016. Then we'll use this here, e 32x minus 2 e 2016x plus 2, parentheses, add a plus c, and that's it. And you know what I noticed? Bad arithmetic mistake, because 2 times 2016 is not 3032, it's going to be 4032. So let me fix this over here, but then of course I need to fix it over here. Oh my god, I fixed it and I still got it wrong. Okay, so now I think everything's looking right. I was a little disappointed that I wasn't able to use the Gaussian integral on here. I mean, I guess that's really wishful thinking. Nothing's squared, so that wasn't going to work, but I do like those ones where they disguise the Gaussian integral. Anyway, good problem today from MIT 2016. Thanks everyone for watching. Have a good day.